All right, so acids. Acids are really what we call H plus ions, and that's going to be the most traditional definition for entrochem specifically. There's lots of different types of acids, but generically speaking, the acids that we focus on in entrochem are all H plus, and specifically H plus in water. A nickname for H plus is called a proton, and that's because hydrogen atoms only have one proton, and that means they only have one electron in their elemental form. However, if you lose your only electron, the proton is the only thing left. So when we say the proton is the nickname for H+, it's really just what it is. Because it's lost its only electron, it has no neutrons, and it's 99% isotopic form of hydrogen 1. So it really just is a proton. We're just calling it what it is, but that is H+. Uniquely, H+ is attacked by water and forms H3O+. So this ability for water molecules to really not like H pluses that are free forces them to attack water. So water can use its lone pairs of electrons to grab onto H atoms and become this new ion called hydronium. So hydronium is really acid in water. So depending on how much H plus you have, that'll determine how much H3O plus will form, because water won't stand for any H pluses to be free floating around in its solution. So again, that's acid in water. And that's really what we're after in this chapter. Base in water would be hydroxide, that hasn't changed. But now hydronium is actually H plus in water. Just think of adding those two together. So as we look at types of electrolytes, just remember that electrolytes conduct electricity, but so can acids and bases. So when we start applying these definitions of strong electrolytes, think strong acids, strong bases, because they're basically the same. Also, when you hear weak electrolytes, think of weak acids and weak bases, because they're essentially the same. So as you look at examples down here, we see that bigger ions like chloride are better at separating. So you can see these chloride ions have separated from their H's. Notice we don't see any H's, we only see H3O pluses. That's because water, as soon as they form, attacks them. But notice over here we see HFs, mostly together. And then every once in a while, we see an F by itself. So seeing them completely separated over here, but only slightly separated over here, that tells us there's a difference in the size of ions that are formed with regards to acid. So it turns out if you're bigger, you're stronger, and you're more likely to leave H plus alone in water. However, if you're smaller, like those hydrogen fluorides, you tend to stick together. So in a way, as we're defining acids and bases, you can think of size to help a little bit, because that can determine strength. So as we look a little bit closer at weak electrolytes, we see that these little HFs are mostly together. It's kind of like in a scary movie, where if you're a small kind of scared person where the villain's chasing you, maybe you're going to be hiding together in the bushes because you're afraid for your life, right? And that's kind of what HF is doing, is most of the time it's stuck together because it fears separation. It feels like if they're not together, they won't be safe. So weaker acids, weaker electrolytes, weaker bases are in that same kind of analogy, that they like to stick together most of the time. 99% of the time, they're together. Only when they're forced to will they separate, about 1% of the time. And that's what we consider weak. And this is also what we would recognize as water insoluble, or a precipitate in the previous chapter. So as you look at these examples, think about, if it's a scary movie, who separated and felt like they could take on the villain by themselves. Maybe they split up in the woods because they thought they would be safer. Who is mostly hiding in the bushes together. Those would be pretty weak and only separate when they have to be separated. Or who is never separated ever, and that's because they're probably gas molecules or organic molecules, with the exception of acids. So as we look at a couple of these examples here, this will be very similar to that beaker kind of question on your homework. Notice here, everybody is separated. Nobody is together. And that shows us that these believe that they're strong, and we could probably recognize that because it has one of the magic five, specifically sodium, potassium, ammonium, acetates, and nitrates. Over here, we do have a little bit of separation, but notice most of the time we're together. And that's what happens when you're weak, is you need somebody else most of the time. And then over here, we're never apart, we're always together, and that's because F2, these are gas molecules, and those are going to be the worst kind. They're never going to separate, they're never going to make ions, so it's going to be non-electrolytes. So the non-electrolyte here, the weak electrolyte here, and then the strong electrolyte definitely over here. So recognizing those solubility issues of the last chapter can really help us a lot in this chapter, if we know how to use that table. As we look at the original definition of acids, that's the Arrhenius definition. He's the scientist associated with this. Really, he just said, think of water. If you think of water, you can think of acidity. So water is HOH. And if you were to split, this would be hydroxide, which is considered a Arrhenius base. And here is H+, and that's called the proton. Just remember that those protons react very quickly with water to make H3O+. But really the definition of an acid is who can give H+ to water. Eventually it turns into H3O+, but really the bare bones definition is if we divide water into two pieces, one side is the acid, one side is the base. We need to know who is capable of giving off those OH negatives, who's capable of giving off those H3O pluses by giving off H+ first. So really the definition of acid is still H+. Just remember that H3O+ is made in water. So if you have H+ ions, you're going to be an Arrhenius acid. That's the idea. To know if you're strong or weak, that really depends on size. So bigger ions tend to be safer, tend to be happier by themselves than smaller ones. So again, here we compare chlorine to fluorine. Fluorine just a 9 proton element versus chlorine that's 17 protons. That tells you chlorine's a whole lot bigger and therefore a whole lot more available in water than H would be from F. So big ions tend to separate more than little ions. That's the idea. So look down on the periodic table to know stronger than chlorine would be bromine, and stronger than bromine would be iodine. We also need to know that some acids can produce more than one hydrogen. Those are called polyprotic acids. Protic just means proton. Poly just means many, so many proton acids is really the idea. So you can imagine with, say, HI or HF, those kinds of things are binary acids, so they have that hydro-ic kind of naming. Both of them were +1, -1, so monoprotic in that sense. But you can imagine H2SO4 as an acid came from the -2 charge of sulfate. That makes sulfuric acid. That's the I ate something icky concept that we saw back in exam 2. So if you have 2 hydrogens, that just means you're diprotic. If you have 3 hydrogens, that means you're triprotic. And it all bases itself on the charge of your partner, the charge of your polyatomic ion or of your monoatomic ion, depending on the case. Regardless, anytime you have an organic-based carboxylic acid, you're going to be weak no matter what. And the reason that you're weak no matter what is because if you're organic, you're almost always a non-electrolyte. Acids are just the exception. They're going to be relatively weak because they can remove their protons. And nobody else can in the organic realm. So as we look at polyprotic acids, just remember that monoprotic is these ones that have a -1 charge. So fluoride, chloride, bromide, iodide, all of those are halogens. HF, the one in blue, is the weakest because it is the smallest. If we get to the series of the hypochlorites, the chlorites, the chlorates, the perchlorates, we're going to get hypochlorous, chlorous, chloric, and perchloric acids. Those are the ones that are next. Notice of those, HCIO, the one in blue, it is the smallest and it is the weakest. So again, size matters for acids. The weaker you are, the smaller you typically are. Then as you see this last one, you may think, well, that doesn't make sense because now you throw a huge one at me and now it's weak. And that's because if you have carbon atoms, you're going to be weak no matter what. Because if you're organic, you're typically a non-electrolyte. There's an exception here because of that carboxylic acid group. Diprotic acids are going to have -2 charges on their ions because they're going to cross over to H pluses in the end. They're going to produce 2 hydronium ions eventually when you put them into water. Things that are relatively weak are things that have small ions like a sulfur, like a carbonate. Those are relatively weak acids. This one, easier to think weak because it has carbon. Most carbons are non-electrolytes, and this one happens to be a carboxylic acid, carbonic acid specifically, and that makes it weak. H2SO4, very strong. It has a big ion, and that's battery acid. That's sulfuric acid, very strong. As you get to triprotic acids, there isn't many of these because there isn't many ions that have a -3 charge that give us 3 protons. So phosphoric acid is really the only one that we deal with in Introchem, and it happens to be weak, which is unfortunate because it is big. And I don't really have a good answer for you of why it's weak other than it really loves, it's like the big teddy bear of acids, it really loves its protons, it doesn't want to give them up. So there's always exceptions to our rules, and that's what makes chemistry so difficult. So of all the big ones, H3PO4 is one of the weakest. As you look at base definitions, really we're just looking at the exact same idea but in reverse. So instead of producing H plus of H2O, we're producing OH negative of H2O. And that's the Arrhenius definition at heart. So as we look for definitions of strong and weak bases, it's really just a matter of who wants to give up OH negative the easiest, who doesn't want to give it up at all. Sodium hydroxide, one of the stronger bases, just because we have one of the magic 5, sodium, potassium, ammonium, would be the positive versions of that. Acetate and nitrate would be the negative anion versions of that. So sodium, potassium, definitely strong, and they're both in group 1. So that kind of hint can tell us that if we were to steal this information from a table we get on the test, really we don't have to look any further than down here. Hydroxides have a category to watch out for. These would be strong, because these would be spectator ions always. These would be soluble in water. And really what you see here is sodium potassium is a group 1 metal, so group 1 metals, and then calcium and barium, those are group 2 metals. So really what we're after is looking for group 1 and group 2, and that's going to be the easiest way to recognize strong, because if you're not in group 1 or 2, then you're not going to be strong. And that's because if you're not in group 1 or 2, you're probably going to be most hydroxides, and most hydroxides are insoluble. So the easiest way to handle these is just think group 1 and 2 strong. So the alkaline earth metals, those are strong. Anybody else, all the way over to that metalloid line, is going to be weak as an electrolyte, as a base, all of which are going to be electrolytes. It's just a matter of who's strong, and that's group 1 and 2. So none of these fit into that realm of non-electrolytes. You do have to worry about alcohols. Alcohols do have a formula that looks like it could get you into trouble. So you can imagine that alcohols and phenols have that ROH, that AROH, or even a carboxylic acid could have an R-carbonyl OH. These OHs are not hydroxides. These OHs are permanently attached, so stay away from alcohol, stay away from phenols, and specifically stay away from this one because that's actually an acid. It has an OH, it just doesn't have the type of OH that can be released in the form of hydroxide. Specifically, this one releases H+, making it an acid. So watch out for these and stay away from these. Those are the ones that are bait because they're not bases. They're acids, and for alcohols and phenols, they're non-electrolytes altogether. So one thing unique about water is it can neutralize itself. So if you have equal amounts of hydronium and hydroxide, that's really what water is. So you can imagine that if water, and this process is reversible, so if water were to attack another water molecule, there is H3O plus. And then what's left over is OH negative, because these electrons will go back to the oxygen, giving it its negative charge. Because you're gaining an extra atom for hydronium, you're going to have an H3O plus. So really this is a reversible process, and this is what we call neutral, because there's this battle back and forth of water becoming acids and bases equally, and that's what we would consider being neutral. So as we look at acids and bases and how they neutralize each other, really this is just a reiteration of our last chapter. Our last chapter mentioned that double replacement reactions would visit this chapter, and here we see them. Their ability to double replace gives us that ability to see that reaction now in the form of neutralization. So H separates from Cl, Na separates from OH, and then we have a partner swapping of the Cl will go with chlorine, and the Cl will go with sodium in the form of chloride ions, and then H will go with OH. So when you write water as HOH, you can see that it had that kind of double replacement concept available to it. And even though we write Na and Cl together, they're really never together, and that's because they're spectators. They'll never need to combine in water because they're strong electrolytes. So as we look at another example with barium hydroxide, realize that the number of hydroxides will determine the number of protons, the number of H pluses, so to speak, that are going to be required. This kind of leads us towards exam 5 because they're mentioning moles. This is a later chapter of the book, chapter 15, and that's why they're mentioning it, even though we haven't really seen moles yet. But as you look at HCl, you would think that's a monoprotic acid. And then as you would look at Cl and realize that it's pretty big, we would also think this is a strong acid. And that's really the difference between last chapter and this chapter. Now we have a better sense of what kind of acids and bases are we looking at. As you look at barium hydroxide, barium is a group 2 metal. Again, this was +1, -1, and that's why it was monoprotic. Here we have barium hydroxide, so hydroxide's a -1, so when you cross that, you get those parentheses that they show up above. +2 probably means group 2, and it is. Group 2 means strong base. Group 1 and group 2 were the strong bases that we mentioned. In a sense, instead of saying monoprotic, you could say dihydroxic almost, if that's even a word, and it's not. But you will see questions that ask you how many hydroxides do you expect, and you would expect the metal to tell you how many hydroxides to expect, no different than the anion would tell you how many protons to expect in an acid. So look for those clues. So as we mix these together, something unique happens, and what unique happens is H goes with OH, and barium goes with chloride. So we get barium chloride potentially, +2, -1 still. That's why it's double replacement. That's why it's an ionic reaction. And then we get HOH, which is just a fancy name for, or at least a fancy formula for water. It's our liquid, and that's why this reaction works. If we look at our spectator ion kind of list of solubility from our previous chapter, you have to be silver, lead, or mercury in order to precipitate, so barium chloride is aqueous, meaning it is a spectator ion. And in this case, it would be a strong electrolyte. And then water, of course, is just water. It's going to be neutral. It's going to be our precipitate in a sense. It's our liquid in this case. This reaction is not balanced because of barium and hydrogen's kind of mismatch, and that's kind of what they're after here. You'll notice that you have 2 bases. You're going to need 2 acids in order to make 2 waters. So this 2OH to 1H was a mismatch. And now as we look at this equation and see this kind of 2 to 1 to 1 to 2 ratio, that's really what moles are. Moles is just a representation of the ratio of how much acid is needed to neutralize the base. So it doesn't matter if this is 2 or 20. If this is 20, then it's 10, 10, and 20. If this 2 was really a 1, this would just be a 0.5, a 0.5, and a 1. So it's all relative to the ratio of the balanced chemical equation. So if HCl is the 0.5, then we're going to need half as much base because it takes twice as much acid. So in that case, it would just be 0.25. And that's really what they're after in a lot of problems as we get closer to exam 5. So in this case, we need half as much because of that 2 to 1 ratio. So if we have 0.5 of our acid, we're going to need half as much base because it's a 2 to 1 ratio of hydroxide to hydrogen ions and hydrochloric acid. So as we segue into our next video, we're going to show you that acids and base definitions can change from their water kind of format with Arrhenius. So we'll catch you then.